Hello everyone, I'm Yongtai from PLCT Lab or ISCS, and today I will be sharing our work on comparing LLVM and GCC performance for RISC-V using SPEC CPU 2017 and SPEC CPU 2006, with focus on code size, dynamic instruction count. Over the past few months, we have built different versions of LLVM and GCC on RISC-V machines. We use those compilers to build the SPEC CPU benchmarks and use each runtime results to conduct some optimization analysis. Okay, here's what I will cover in this talk. First, I will explain why RISC-V and compiler performance are important. Then I will introduce our methodology describing how we tested LLVM and GCC. Next, I will show the results comparing code size and dynamic instruction count, as well as the impact of the RISC-V vector extension. Here, we will see the performance gap between LLVM and GCC. After that, there are two specific case studies, the present possible optimizations, and finally the conclusion and the future work. Okay. Now let's see the background. RISC-V is growing fast in both embedded systems and high-performance computing. For embedded systems, code size is critical important. Those systems operate under several considerable resource, where smaller code size usually means less resource uses. For high-performance computing, reducing dynamic instructions count directly enhances throughput and performance. SPEC CPU is a well-known benchmark suite. It includes different types of programs that help us compare how LLVM and GCC perform. Next, I will explain how we conduct our test. We built the compilers and benchmarks on RISC-V machines, then executed the tests and collected performance data through QEMU on x86 systems. Finally, we developed an automated tools to do this. Here are some details. All RISC-V builds were performed. Performed natively on a 64Q Milk-V polling box, and the performance data were generated from those two specific compiler commits. And OFAST and FL2 flags is used for C and C++ workloads, while only OFAST enabled for Fortran codes. We configured two build targets, RV64GC, ZBA, ZBB, ZBS as the scalar baseline, and RV64GCV, ZBA, ZBB, ZBS as the vector-enabled target. Okay, after completing the builds, we prepare the SPEC CPU runtime environment using this single-line commands. This screenshot is the run dictionary for 548 exchange 2. Okay. And then the spec invoke command will tell us exactly how the test is run. As you can see, there's only a single number 6 as the argument for this case. Now all the preparation has been made. Next step is run and get the data. For code size, strip and read the binary field size, it's easy to do it by a Python script. The dynamic instruction count will capture using QEMU's built-in INSN plugin, just like this. Okay, here are some links about the plugin. And we built a tool to run those tests in parallel using QEMU. It saved many time. Here is a GitHub reporting and some screenshot about this tool. Now let's look at the results. For code size, LLVM outperforms the GCC in 70% of cases on C and C++ workloads. But for fortune code, however, LLVM tends to generate larger binaries. Okay, this table shows the raw data, which can be viewed by scanning the QR code. At the top of the table are the C and C++ benchmarks, and at the bottom are the Fortran benchmarks. By the way, some benchmarks contain both C and Fortran code. I classified them based on whichever has the most lines of code. It's easy to say that in extreme case, for example, the benchmark 508, the binary field generated by LLVM is only 64% the size of GCCs, while the benchmark 503, LLVM's code size is even 20 times larger than GCCs. Okay, next let's look at the dynamic instruction count. The bar chart shows LLVM's dynamic instruction count relative to GCC. The unfilled bars represent tests for the scalar target, while the gray bars indicate case when the V extension is enabled. It's not difficult to say that for integrated benchmarks, except for 548, LLVM and GCC sources have small difference. Through LLVM often has a higher dynamic instruction count than GCC. However, for float point rate benchmarks, the solution differs. For some benchmarks on the scalar target, LLVM performs worse than GCC, but on the vector target, LLVM outperforms GCC. This table presents specific data points. As previously mentioned, for the integrated benchmarks 525 and 548, LLVM exhibit a higher dynamic instruction count than GCC on both scalar and vector targets, whereas for the FP rate float point rate benchmarks 549 and 554, LLVM performs better than GCC while the vector extension is enabled. Now let's see the impact of the V extension. Both for GCC and LLVM enable the V extension achieves greater instruction count reduction in float point rate benchmarks. And LLVM have larger avenue reductions in instruction count. Okay. Now let's see a specific benchmark 548. It's a Sudoku solver writing in Fortran, and it has no floating point computation and heavily relies on recursion. LLVM execute twice as many dynamic instructions, and moreover, this behavior is not specific to RISC-V. It also holds on other architectures. Okay. All the later tests we were conducted on the RISC-V 64GC platform, and mostly use object dump and perf to dig into things. Now here are how we complete complete and run these benchmarks, it's quite simple since it just has one source file. Okay, all right. It's a perf report, and it's easy to say the hot function is totally the digit 2, and in GCC's version, it got split into specific version digit 2 dot constprop dot 1, constprop dot 2 dot 3, and so on. The obj dump results so the code lines of those GCC specialized functions are much smaller than those in LLVM. Okay. The presence of the dot constprop in the function names clearly indicates that this is a result of GCC's interprocedural constant propagation optimization, the IPACP. A primary effect of this optimization is branch emulation, which directly contributes to the reduced stack code. And the optimization path in LLVM is IPSCCP path. On one hand, when we disabled this GCC optimization with the F no IPACP flag, the dynamic instructions count almost doubles. Meanwhile, on the other side, running the IPSCCP path through OPT, the dynamic instruction count we can solve a specific version of the digit 2 function pop up. There's digit 2 specialized dot 3. And we tried to add an extra IPSCC path to the path pipeline and checked each person. It make a difference as long as we placed it after the inliner pipelines. And those next two slides show how well this thing works. Okay. But running IPSCC path twice cause a compile time regression. The good news is that running argument promotion before the original IPSCC path makes sense, as the following PR does in the L2 pipeline. In fact, there's an argument permission path in the inliner pipeline mentioned earlier, and running an actual argument permission path has less compile time impact than an actual IPSCC path. Okay, next let's take a similar look at 473A star. Where the RVM's dynamic instruction count exceeds than that of GCC. By the way, 463, this benchmark is from SPEC CPU 2006. The test methodology and tuning I mentioned earlier apply equally to both SPEC CPU 2017 and SPEC CPU 2006. Here are the proof report results. You can see the function release point accounts for a much larger fraction of dynamic instructions in RVM than it in GCC. And let me show you the source code and how each compiler translates it. In the source, the most notable feature is an earlier exit branch right at the start of the function body. And now let's compare the the generated code. On the left is GCC switch, on the right is RVMs. In GCC's output, entering the earlier exit branch does not spill any of the cohesive registers. In RVM's output, however, all of the S0 to S11 registers are saved on entry and restored before exit, even though the earlier exit paths only actually use S1. The difference stemmed from the two compilers' implementation of the shrink-wrap optimization. GCC GCC's shrink-wrap optimization split store and restore points, while RVM trading off computing compile time cost impact on debugging tools like unwinding and so on. Use simple shrink-wrap optimization, and that does not split those points. For this specific case of 73A star, a small menu tick in the RVM generated release point function, moving the SD instructions to after the early exit branch can reduce the benchmark's overall dynamic instruction count by roughly 4%. In fact, if you move the if sentence out of the function, you can get a performance improve. Regardless, we now know that for 73A star is sensitive to shrink-wrap optimization, and you may notice that there's several improvement PRs are currently in progress. Okay, so finally, in conclusion, we saw that RVM can build the full SPEC CPU suite even with many function codes on both RISC-V 64GCB and RISC-V 64GCBV. That means RVM Flan is ready for real-world RISC-V work. We also found that for C and C++ code, RVM usually makes smaller binaries than GCC, but for Fortran, it can get quite a bit bigger. Performance-wise, GCC still has a slight edge on iterate benchmarks, while RVM's auto vectorization really shines on floating point benchmarks when the vector extension is on. And this slide links to the Google shares that the data we've been talking about. Thanks everyone.